Good morning. Welcome to Algor's Tuesday at 10 webcast. Today's date is April 17, 2007, and the subject is working with composite materials. My name is Joe Stefanelli. I'm an application engineer here at Algor. I'll let my partner introduce himself.
Good morning, and I'm Marwan Azam, also an application engineer with Algor.
Okay, so we're going to look at the various analysis types for which composite elements can be used and the way that they're defined within the models, the various properties and options that are available. We have a few different examples to show you, and right now I'm going to jump over to the computer and we'll let Marwan start off.
First of all, we're going to show you what, like Joe said here, what kind of analysis types we can use, how to set up composite elements, and so on, some basic things about composite elements. Really, some contact information first. In US and Canada, you can reach us at the toll-free number 1-800-48-ALGOR or the phone number 1412 area code 967-2700. Our fax number is 412-967-2781, and our email is service@algor.com. So anytime you need technical support, have any questions of any kind, you want to use these phone numbers, fax number, and email address. Also, other resources for the Algor software are webcasts like these, which you can access on our etechlearning.com. And of course, the first thing you want to do is check out our documentation by accessing the help menu inside of FemPro. Next slide, please. The analysis types available for composite elements are static stress with linear material models, linear dynamics, and by those we mean the natural frequency analyses and other vibration analyses such as random vibrations, frequency response, response spectrum, and so on. All these fall under the linear dynamics analysis types, and they have composite elements available for use in them. And last but not least is our mechanical event simulation, MES analysis type, that also has the composite element as a subcategory of the shell elements. Actually, you would have to go to enhanced shell elements and composite, whereas for the linear analyses, they are their own element type and not a category, subcategory that is. Just as an overview here, we're not going to go into too much detail going into composite theory and so on. The two main types of composite elements are the thin composites, which use the Kirchhoff theory. These are layers of more or less the same thickness. You stack them up on top of each other. It supports the Taiwu maximum stress and maximum strain failure criteria, and it has core crushing stress capability. It calculates the core crushing stresses. The other kind is the thick composite. It uses a different theory. This uses the Mendlin theory. Typically, when you're using thick composite, you have one layer which is much thicker than the other layers. It's like a core layer and surrounded by skin, so to speak. This supports also the Taiwu maximum stress and maximum strain failure criteria, and it also has core crushing stresses calculated. And by the way, whenever you want to use those failure criteria and the core crushing criteria, there's more input required on the user's side so that it knows how to calculate the numbers. Basically, a composite element is one part. So the mesh looks like a plate element. It's a planar. The element is 3 or 4 sided, 3 or 4 node element. Of course, the element has to be in one plane. The element itself has no geometrical thickness. The thickness is entered under the element definition. That's where you specify how many layers you have and the thickness of each layer. And in the composite element, like this says, you have one part with multiple layers. And you keep stacking them on top of each other. Let's go to the next slide, please. There are certain axes used for composite elements. In general, there are 4 types of axes. There's a global axes, X, Y, and Z. These are shown in the mini-axis display. These are just the main axes in the software. There's the element axis, ABC. There's the laminate axis, which specifies how the whole element is oriented, and there's the lamina axis, 1, 2, 3, and we'll elaborate on all these in the next few slides. And the lamina axis basically specifies how each layer is stacked, at what angle is it stacked relative to the laminate axis. So really you have to define the laminate axis and then the laminate axis, which is relative to the laminate axis. It does get a little bit involved, really. There's a couple of ways to define the element axes A and B. Either you orient, the first option is to orient the I node. So there's a point, which is the orientation point. And then from that, there's two options. Either to orient, the option one is to orient the I node. So this means that the closest node to the orientation node will be the I node. The second option is to orient the IJ side, meaning the IJ side would be the one closest to the orientation point. And there's actually the third option, which is the highest surface number. The highest surface number will define the IJ. But really, in our composites, we don't really care so much about the element axes A and B. We care more about the lamina and laminate axes, which we'll talk about in the next couple of slides here. The laminate axis, which really is one set of axes for the whole part, and off of which you specify how the lamina are stacked and rotated. There's a couple of options. Option one is a specified angle from the AB axis, which we described in the previous slide. So you specify a certain angle from the AB axis. This works well for a very structured mesh, where the IJ side, so to speak, is always going to be pointing in a certain direction. And in fact, one of the examples would use that. But in case you have an unstructured mesh, you don't want to go with that, because if you go with this option, option one, which is a certain angle from the AB, remember the AB axis depends on each element, how each element is oriented. Okay? Now, like I said, if the elements are all oriented similarly due to a structured mesh, that works well. But if it's an unstructured mesh, then you don't want to use an angle. You want to use a specified vector to define the laminate axis, small x, y, and z. This will set them all in the same direction, regardless of how the element itself is oriented. So once you define your laminate axis, the next slide will show us how we define the lamina axis, which is basically an angle relative to the laminate axis. This is all done in the element definition window or dialog box. So once you define the laminate axis, you start laying your lamina, and each one can have its own lamina axis, which is just an angle relative to the laminate axis. Next, we're going to go through some examples. Our first example is going to be a linear static stress example. It's going to be from a CAD model. The examples are going to be simple, basically. Joe is going to bring up SolidWorks. I built a very simple model here in SolidWorks, basically a 90-degree curved part. And we're going to use that for a thick composite. So inside of SolidWorks, all we do here is go to Algor Mesh. There's an Algor menu item up. And we just bring the model into Algor. We set the analysis type to linear static stress, or static stress with linear material models, which is the first option. Hit OK, and the model comes into Algor. What we're going to do with this model once it comes in is mesh it. Here's the model. Of course, it has a certain thickness. This is actually a solid model. It's not a surface model. So it has a certain thickness, but really that doesn't matter, because what we're going to do is we're going to mid-plane mesh this and set our own layers with their own thicknesses. So the first step is to click on the mesh button here and change the mesh type to mid-plane and hit OK. We're going to go with the 100% mesh size.
Okay, let me go ahead and hit the mesh button.
Yeah, we're going to hit the mesh button. I'm sorry. OK, we'll just accept these settings and not do the meshing itself. And actually, to demonstrate the point here, what I'm going to have Joe do is select the point kind of in the middle of the whole part here. If you rotate it a little bit so we can see the lengthwise, yeah, this is the z-axis, I believe. If you just select the point in the middle and set that as a refinement point, yeah, somewhere here in the middle, just to kind of, because this turns out to be a very structured mesh. even though it came in from a CAD model. Just due to its geometry, it comes out pretty structured. So what we're going to do is specify a refinement point just to throw the mesh off and get some differently oriented elements, some triangular elements and so on. So we'll use a radius divide here. We'll set a radius of 3 inches and a divide factor of 3 as well.
All right.
And we'll redo the mesh and zoom into that area and see how that mesh changes. Right now it's a very structured, parallel lines. So if Joe zooms in, maybe rotate that a little bit so it's clearer. Okay, this is a very good view. You can see if it weren't for the refinement point, the mesh would be very structured, but we got some differently oriented elements here. Next, we're going to go into the model tree and set our element type to thick composite. You see that we have 2 options under element type. We have a thick composite and a thin composite. We're going to select the one that says thick composite. And you notice that our material definition gets grayed out because for composite elements, you define the materials inside the element definition. So everything is done inside the element definition. The orientation, the thicknesses, as well as the materials, everything is done inside the element definition. So we'll double click on that. We're going to leave the element normal point to 0, 0, 0 under orientation. And first of all, we're going to go to that last tab, which says, let's go to the last tab here.
Orientation.
Orientation. Okay, we'll leave the, I'm sorry, I'm not wearing my glasses. We'll leave the element normal point to 0, 0, 0. That works out pretty good. We're going to change, this is the nodal order. We're not going to touch that. So we're not too concerned about the nodal order. So we'll go back to the first orientation, the general tab. And that's where you define your laminate axis. Remember from the slide, we had 2 options, either as a specified angle or as a vector. Like we said, the specified angle is not going to work well for this example, so we're going to go with a vector and choose the vector 0, 0, 1. So now our laminate are oriented. The small x-axis would be along the global z-axis. Now if we go to the next tab, the laminate tab, that's where you actually define your layers. This is it in table format, so you can add as many layers as you want. Stack them up on top of each other, starting from the bottom, which is closest to the element normal point, and stacking layers on top of each other. In this case, we are going to have 3 layers, actually. The first layer, since this is a thin composite, let's make something that resembles like a skin and a thick layer in the middle and another skin. So let's make the skin 0.05 inches in thickness. We'll keep the orientation at 0 for that first layer. And for the material, let's click on material. And this will bring up our material definition window, which actually, when you are using composite elements, you are using, by default, orthotropic materials. They're not isotropic materials. We're not going to select anything from our library for this example. Our next example, we'll select something from the library, which actually contains mostly wood-type materials. It doesn't have any metals. So really, it's a very good idea if you are going to do composites to create your own material library, and this way you will save yourself a lot of trouble of entering numbers every time you do a model. So let's click on customer defined, go in there, and start entering the numbers. For density, really, we can input anything here. We can input, let's say, 7e to the minus 4. For the modulus of elasticity in the local 1 axis, E1, we're going to enter 2.21 e to the 6. For the local 2, we're going to enter something much smaller, really, which is 0.173 e to the 6. And typically that's how it works when you have composites. You have, the strong axis and the weak axis. The next one here is the Poisson ratio, the 2 Poisson's ratio. The first one, we're going to set that to 0.426. And the second one, we're going to set it to 0.043. Thermal coefficient of expansion, let's set those. Alpha 1 is 2.1 e to the minus 6. And alpha 2 is actually much bigger, is 16.7 e to the 6. Or e to the minus 6, I'm sorry. E to the 6 would just be huge. What's next here is the shear modulus. Let's set that to 6.16 e to the 6. And this one to 0.15 e to the 6. And the last one is 0.037 e to the 6. You notice there's a lot more input involved when you are using such materials than you typically have with just an isotropic material. The next few tabs here are for the allowable stresses. If you want to use, if you want to calculate failure, then you would want to come in here and type these allowables in. And I believe our third example, we'll type some numbers here and look at the failure criteria. For this for the first couple of examples, we're not going to do that. So we'll leave those at 0. So let's hit OK on this material. And actually what you can do here is you can copy one row into the other, and then we can insert a row in the middle.
Okay, from row 1.
From row 1. I think this should work fine.
Yeah, it's going to go before.
But they're the same. And maybe we can enter an angle of 90 degrees for this one. And we'll insert a row in the middle, and that's going to be our thick layer.
Okay.
And we'll make that 0.125. And we'll leave the orientation at 0. We'll go into the material. And we also use a custom defined material here. And actually what we can do is we can make those similar to something which is isotropic. So we'll enter the same values for E1 and E2, maybe 30 e to the 6 for both these values. And we'll set the Poisson's ratio to 0.3 for both. We'll leave the thermal coefficient of expansion. We can use 1 e to the minus 6. And let's see, it probably calculates those if you leave them at 0. Or we can use a g of 6 e to the minus 6 G12 here, which is the shear.
6.
Yeah, 6 e to the 6, I'm sorry. And we'll use that same number for all of them and hit OK.
Now, we didn't include a density, but that's not a problem if we're not going to have a gravitational load or a centrifugal load.
I'm thinking of putting some kind of thermal loading here and see how. Actually, we can do a couple of load cases here. We can do thermal and we can do a pressure. So we'll hit OK on that. And let's just grab one edge of this, one of the long edges, and fully fix it.
Okay. One of the long edges.
And apply fully fixed boundary conditions on that. And select the surface, the big, well, it's all one surface, and apply a pressure of 1 psi. Normal.
Okay.
And let's go into the analysis parameters. Actually, and add a row here and set the thermal multiplier to 1.
Which row?
Second row, I'm sorry, second row. So our second load case will be the thermal, and maybe we can set the pressure multiplier to 0 for that, just thermal, and go to the thermal / electrical tab and set a temperature of 50 degrees. So that would be our delta T, basically 50 degrees. And we'll hit OK, and we're ready to perform the analysis at this point. And the reason I wanted to use thermal loading here is you'll see how it's not going to deform uniformly because it is a composite with different coefficient of thermal expansion and so on. Okay. First of all, let's look at the way the model is set up. Let's go to results options and show the orientation marks. Results options.
Display options.
Display options. Show orientation marks and show the material axis. And if you zoom in to that refined area, I don't know, can we see that?
It's very hard to tell, but
it's very hard to tell. But what I wanted to show you is that regardless of how the elements themselves are oriented, the axis is always pointing in the z direction.
let me see if I can.
Okay, yeah, here we go. All these elements here, if you remember, they're not fully, rectangular, pointing, all parallel lines. They're not, but you can see that the axis is always in the z direction. That's because we specified that vector in the element definition. Let's look at a couple of results that we get out of it. This is the, let's turn this off so we can see what we have. Let's go then to the first load case. That's fine. You can look at the stresses, of course, and the displacement, just like any other element type, but under results options, let's look at the stresses. We are looking at the stresses.
Von Mises now.
Yeah. If we look at composite options, you can, if you look here, we can look at the results for core lamina, Wirtz results for specific lamina, so you can look at each lamina separately. Lamina 1, if you hit apply, it shows the results for that. Lamina 2 and lamina 3. So you can look at the worst, you can look at each lamina individually, and you can look at the results for the core lamina. The default is the worst results. So that's how that is different from a regular, say, plate element. Let's do another example here. That's going to be a hand-built example of a disc-shaped object. And what we want to demonstrate in that example is the structured mesh. So that'll be a quick one. So Joe, why don't you just go ahead and add a line in part number 1.
Okay.
And we'll make that, we'll uncheck construction. We want it to be an actual mesh line. That's going to start from x equal to 12. So at 1 foot, hit enter. And it's going to go to 24 inches.
So x equals 24?
24, x equal 24. And that's our line. We'll hit x to exit out of that. We'll select that line and divide it into 5 lines by right-clicking. So Joe selected the line, right-click, divide into 5. And then we're going to rotate that around the z-axis. So we'll select all these lines by doing a rectangle select of lines, right-click, rotate or copy, and we'll make 48 copies and join all copies. The total angle is 360. And the axis of rotation is the z-axis, and the center, of course, is 0, 0, 0. And we'll hit OK, and that will create our model. So we're going to set the analysis type. It is static stress with linear material models. Our element type is going to be thin composite. And we're going to go into the element definition to set the layers and so on. let's go to the orientation tab and set our element normal something in the negative z. Let's say 0, 0, minus 1. And go back to the general tab. In this case, we can use a specified angle. And in fact, we can leave that at 0. And the reason we can do that is because it's a very structured mesh. And once we run the analysis, we'll go again to show the element X or the laminate axis and show how that is very uniform, even with using an angle. Let's go into the laminate and specify maybe 3 layers here. And let's make the thickness 0.1 for the first one. And we'll make them all 0.1 inches. The only difference between them is going to be that they're going to be oriented differently. So one would be 0 angle, the other would be 45, and the third one would be 90 degrees. So we got 3 layers stacked on top of each other in different orientations. As far as the material, let's go in here and select something from our library. This way we don't have to enter all these numbers. Let's select the first one on the list here.
The ash.
Yes, the ash material. Great. And we'll do that for all 3 of them. Actually, we could have copied them. Yeah, if you could leave the rows. Yeah.
Okay, well, the other thing you can do is, let me see. No, actually, it's a little different for MES. We'll look at a different selection method in the MES example. So we'll just pick this as ash again. And one more time. It's the stuff they make baseball bats out of. Okay.
Yeah. And the way we're going to load this and constrain it is, let's constrain all the inside nodes here. So Joe can display this in the XY plane. Or actually, yeah, you can either use circle select or you can use a chain border select. Let's actually use a chain border select of lines. And if you click on one line, it's by default it's going to select the
it's not doing
the interior. So we're going to go to selection. Actually, it's a little different.
It's not doing it. It'll do the outside.
No, actually, Joe, this is very interesting because they changed that for version 20.
Okay.
And version 19 and before, depending how you click on the line, it's either going to select the inside or the outside. Right now, it's more consistent because if you go to selection, up on the main menu, and go to mode, select chain border, and click on select larger chain border.
Okay.
So that's always consistent now. No matter where you click, it's going to select the outside. Now you're going to right click and select sub-entities and nodes. And we're going to fully constrain these nodes. And with the same selection method, we're going to select the outside chain border of lines. Right click and select sub-entities, vertices. And this is a very, very convenient way of selecting nodes that would otherwise be very, tedious. And let's apply a 1 pound or maybe a half a pound force in the z direction on each one of those nodes.
Okay.
So that'd be 0.5 and the z direction. And we'll hit OK and go ahead and perform the analysis. And these are the kind of stresses we get out of this, even though this is a symmetrical model. If this was plate elements, straight plate elements with isotropic material, you wouldn't expect to see such a pattern for stresses. It should all be concentric circles. And again, if you go to display options and show those these axes here, and maybe show the mesh and zoom in, you'll see how they are all uniform. They're pointing all uniformly around the mesh. That's because it's a very structured mesh. So you have to be aware what your mesh looks like to be able to orient the lamina appropriately to know which selection, which orientation method you should use for your X, Y, for your laminate axis X, Y, and Z. That takes us to the end of the second example. I think Joe has an MES example for us, so I'm going to head over to the computer and we'll go through the mechanical event simulation example.
You just give it a name.
You're going to build it by hand?
Yeah, it'll be a hand-built model.
Okay, so we're doing a file new, and we will do give it a name, save it.
Okay, and we'll set the analysis type to MES, nonlinear MES. Okay. Now, like the previous example, we're going to start with just drawing a simple line. So we have the line draw command and make sure the construction button is turned off because we want to create an actual FEA line. Part 1, we're going to start at a coordinate of -300. Go ahead and hit enter. And then we're going to end that at +300. Okay, and for now, we'll close the dialog and close the view. Okay, we want to select this line and divide it into 8 pieces. Okay, now to make matters easier, there's a little toggle we can hit that'll show the vertex locations. Okay, and there they are. Now we're going to go back to our line command, and this time we're going to change to part number 2. And we want to select the third node from the upper left end of the, right there, as our starting point. And we're going to go relative distance -2 in the Z. Okay, and you can hit escape once and go over to the opposite node, yeah, third from the other end. Same thing, -2 in the Z. And that's the end of our line command. You can go ahead and exit out of there. Now we want to select those 2 lines and divide each of them into 3 pieces. So right-click, divide, 3. All right. So this is the basic outline we're going to start with. We'll now extrude it in the Y direction. So we need to select all of these lines. And we're going to do a move or copy, right-click, move or copy. And let's do copy join. We want 30 divisions. And we're going to go a total distance of 24 inches in the Y direction. And hit OK. All right. Now, once we set our element type to shell elements, they'll shade in. So let's go ahead and set both of those at the same time to shell elements. Remember, at the onset, Marlon indicated that in the case of a nonlinear analysis, composites are not listed as a separate element type. Rather, they're a subtype of the shell element. When we go into the element definition screen, we'll do these individually because they're going to have different laminations. Go ahead into the first part. And over on the right side of the dialog box, we need to change the type of shell from original to enhanced. And then under the material model field, we change from isotropic to composite. There's also a temperature-dependent composite available. We're using the regular composite option. Okay? Let's go ahead and click OK there.
Oh, I changed that.
Okay. Let's go to the Orientation tab. And we want an element normal point of 0, 0, -1. So -1 in the Z direction. let's see, what is the bottom there? Nodal order. Let's go back to the General tab. The orientation of the material axis direction, in this case, we're going to use global Y as the option. Under the pull-down menu, you can see it's a little bit different than the way it's defined for a static analysis. But in this case, essentially, we're saying a vector in the Y direction so that all of the laminae will be rotated relative to that direction. So if the rotation angle is 0, the grain is going to be running the length of the extrusion that we made. That'll be the strong axis. Okay, let's go to the laminations, or the composite tab. And once again, we have our table format. We're going to have 3 layers in this particular example for part 1. And let's set the thickness to 0.05 for the first and last layer. And actually, let's insert one more layer right there at 2. I'm going to go with 4. Okay. For the second and the third, we're going to go with 0.1. And our orientation angle is going to be 0 for the first, minus 45, plus 45, and 0 again. So the skin has its strong axis in the direction of the extrusion, and the other ones are rotated plus and minus like 45-degree bias. For our material, let's go ahead and pick the first one. And here this dialog is a little different than what we saw in the static analysis. We have a submenu which basically keeps a history of prior laminations. Now we haven't defined any laminations yet, so this field is grayed out. But it gives you a convenient way of reselecting a material that's been previously selected. So let's click on the Modify button. Okay, it's coming up. All right, now in this case, I actually created a library of materials, which you might want to do as well. And we're going to select an alternate library from the pull-down, and I named it Composites. And we have 3 different materials in there called Core, Layer 2, and Skin. We're at the first layer, so this is going to be a skin layer. And if you just kind of scroll over, you can see that the properties have already been defined for us. And in addition to the modulus, I have failure criterion already defined. So we have allowable compressive stresses and tensile stresses. I thought we did anyway.
Well, I think if we hit the edit, we'll be able to see more.
Okay. Yeah, check the there's the allowable stresses. Okay, so they're already defined for us. We don't have to type them in every time. We'll go ahead and accept that. And hit OK one more time.
That was the...
Oh, yeah. Change it back to the skin because I thought we were overriding
Once you go into edit, it's going to say, okay, you might have made a change, so I'm going to call it customer defined.
Right, even though we didn't change anything.
Yeah, I should have hit escape and not OK, but that's fine. We select skin again, and we hit OK now.
Right.
So now, it remembers that you've already used one material, so it's added to this drop-down menu.
That's right. Okay, go ahead and click OK here. And for our second layer, we're going to go back to the same library. We'll have to add, in this case, because we don't want to replace our skin entry. We want an additional one. We'll go back to our composite library and choose layer 2 as the part once it comes up. Okay, we'll accept that. Okay. For the next one, it'll be a little easier because layer 2 is already defined. So we just pull it from our menu. And finally, a skin again on the bottom.
Much faster, too.
Yeah, so that finishes the definition of the elements. We can go ahead and click OK. We're going to go through the same process for the legs, which are both part 2. The stiffeners or ribs, you might want to call them, for this. This is going to be a cantilever beam. So we'll go into the element definition screen again. Set our enhanced shell composite type. We're going to use the same axis definition of global Y. Actually, do that on the first tab. Okay, you can set that while you're there, -1 for the normal point. What that's basically going to do is define the bottom of the top part as the bottom, layer 1, and the inside 2 surfaces of the 2 ribs will both end up being layer 1, because those are the sides that face the element normal point. Okay, global y-axis we're setting again. And let's go to our laminate or composite tab. And let's see, this one we can start with a thickness of 0.5, an orientation angle of 0, and the second row we're going to be 0.1 and -45. Let's add a thicker core layer for the third row. We'll make this one 0.2, and once again an orientation of 0, and basically the mirror image of that. So we want 4 to be a copy of 2, and yes, 5 to be a copy of 1, and that'll be +45. Okay, so again, I'm taking the skin and the core and I'm orienting them longitudinally and using a plus and minus 45-degree bias for the other plies. And for the materials, they'll be easy because it'll remember from the first, or does it? Yes,
yeah, it does.
Okay, so we're going to have a skin layer to start with and a skin layer to end with. Layer 2 for the, go ahead, do that. Layer 2 for the second and fourth. And then the material we call core we'll add. And this actually is defined as an isotropic material. It's using an orthotropic material model, but we've set the Young's modulus to be the same, tensile strength and so forth to be the same in every direction. Okay. So it's going to act like, maybe it's a soft plastic material or something that has relatively isotropic properties. Incidentally, before we go any further, a general comment while I'm thinking about it. There are a couple of different ways of handling composite materials, and one approach that's been taken is if you have a composite, a given stack up of material, say fiberglass type circuit board, glass epoxy or whatever, and you know the behavior of the sandwich of maybe 5 layers, but you know its behavior as a whole, you can treat it as a regular plate element or a regular shell element that's orthotropic. However, if you want to do design of the actual composite itself and play with the rotation angle, the orientation of the grain in each individual lamination, play with the lamination thicknesses and formulation, this is where you want to use the composite elements or the composite shell element option. But again, if you know the properties of the sandwich as a whole, you can choose the alternate approach of not defining it lamination by lamination.
Or sometimes what you can do in other situations, but similar, is if you have some kind of honeycomb or some kind of complicated geometry that if you're going to model that using, say, bricks or plates, it's going to be very complicated. You can do like a sub-model of a 1 inch by 1 inch, do a lot of analysis on it, study the behavior, and say, okay, well, this seems to be, behaving at such and such, orthotropic, I'm going to build my model using these kind of derived properties from my small model.
Right. That's a very good example. Yeah, and that'll cut down your final model size to something manageable, without millions of elements in it that might be needed for something as complex as a honeycomb shape. Okay, that completes the definition.
Any failure criteria?
Oh, failure criteria. Yeah, we need to do that in the other one too. Thanks for reminding me.
Sure.
The data that I entered is allowable stresses. I didn't enter SIWU criteria, so we're going to choose as our option maximum stress for the failure criteria. We need to go back to part 1 and do that as well, if you didn't already.
No, we didn't. So that's under element definition. And
I think it was in the laminate screen, right? Or the composite screen. Maximum stress failure criteria, right above the table where you define the laminations. Okay. Now, let's do an XY view, XY top view. And we're going to box select some nodes. We're going to take all the nodes on the top edge. And let's add nodal force. All right, and I believe there's 17 nodes, so we want a total of 50 pounds. So let's type in 50 divided by 17 equals, just hit the equal sign, there you go, and that calculates for us what the force per node is for a total of 50. And we want 0, 0, minus 1 as our vector, so it's going to act in the minus z direction. You could have also made the magnitude negative and just used the z button. Okay. Let's grab the nodes on the opposite end. And we're going to fix those. So it'll be fully constrained. Okay. So basically we have a cantilever beam. Fixed on one end, a downward force on the opposite end. Let's go to our analysis parameters. Okay, so here's our load curve. We're going to need to add 1 row to that. And we'll just do 1 second and a multiplier of 1. So it's going to take 1 second to ramp the load up from 0 to 50 pounds. The event duration is 1 second, which Marlon's already set. We're going to use a capture rate of 20. So we'll get 20 time steps per second, or a total of 20 in this case. Let's go to the advanced button. And I want to relax the convergence criterion slightly so it runs a little faster. The displacement tolerance there in the middle, we're going to change that to 0.05. So not a severe relaxing, just a little bit. Okay, and then we'll accept that and accept that as well. And the analysis is ready to run. And despite the 20 time steps, this should run in about a minute or less. Okay, that was pretty quick. All right. So as in the other examples, we're going to see the same types of displacement and stress results with one additional item. If we go to the results menu, let's just zoom in a little bit. And stress. And down at the bottom, there's a composite pull-out menu, and we have our failure index because we did specify failure criterion. Now this will give us an index. Basically, the highest values are going to be the ones with the lowest stress. So it's like 241 times the applied stress would be required before failure would occur. And the minimum there is 5, so we have a significant safety factor. Now this is one case, though, where we'd probably want to do 2 things for our presentation. we'd probably want to reverse the color scheme to put red at the minimum magnitude rather than the maximum, because in this case, lower is worse. So let's go to the display options and plot settings. And we're going to reverse. There's a little button on the bottom to reverse the colors. Okay, and say OK. And the other thing we're going to want to do is probably look at individual laminations to see if there's a failure problem in the interior or on a particular lamination. So we'll go to the composite options. We'll look at results for a specific lamina. And if we apply, we'll see it for the first one. And what are we at here? See, 1.13. We're coming very close to failure on the skin. Let's go to the second one. 2 point something.
2.8. Let me do this.
Okay, so a little better there.
Closer to each other.
Yeah.
So we can see them.
Okay.
That's much better than 1.13. Almost double as much.
And the third one, we're at again just a little over 2. And finally, let's see, we have 5 layers in this one. Right, I think, yeah, because we have the core layer. So we have one more after this. And here we're at less than 1. So we're actually seeing a marginal stress here, something slightly beyond failure on a single lamination. Okay. Let's go back to worst results, and we'll just take a quick look at the displacement. And go ahead and close that dialog. Yeah, magnitude's fine. And what are we seeing here is the maximum displacement.
That's about 0.164 inches.
Okay, so between 1/8 and 3/16 of an inch displacement. This is a relatively short beam. It's only a couple of feet long. All right. I think that pretty much covers the topic. Go ahead and pull up the last slide. Okay, and once again, contact information for you. The phone numbers where we can be reached, and the email. We do ask that when you contact us by fax or by email that you please put your license number in the subject line so that the issue is properly logged and routed. The websites that are available for additional information as well. So with that, we thank you for your attention. I hope that you find the information useful and wish you success in your future modeling efforts with Algor.
And
thank you.
Thank you very much.